Hi, in this video, we want to take a look at the correlation between distances and our dendrogram heights when we're doing hierarchical clustering. All right, so specifically, we're going to be looking at cophenetic correlation. All right, so cophenetic correlation is where we take the original distances between our row observations and we do hierarchical clustering. Then we take the height that is the lowest height where the 2 points of interest are in the same cluster on the dendrogram. We take that lowest common cluster height on the dendrogram. We take the distance from our original distance matrix, and then we take the correlation between the two. When I say correlation, that's going to be Pearson correlation, and that is the cophenetic correlation. All right, so why do we want to do this? Well, if our cophenetic correlation is higher, that's an indication that our dendrogram is consistent with the distances that we are observing with our real life data. And so that gives us confidence that we've picked a good way to build a hierarchical clustering. All right, now why do we do hierarchical clustering? All right, so first and foremost, we're interested in analyzing a taxonomy structure into the rows of our data. All right, that's where the taxonomy indicates which rows are more similar to each other, which ones are different. Another reason why we'd want to do this, the rest of these reasons are for regular clustering, any type of clustering. But we can use hierarchical clustering to accomplish this, just like partition clustering or model clustering. We want to segment our data. And so in that situation, I want to break up my data into groups, and each group will be handled differently depending on what's going on. We want to do outlier detection. We want to detect subpopulation. So in this situation, I have my data, and I believe that there are subpopulations in my data, but it wasn't recorded in my data set. In that situation, what am I going to do? Well, we could use clustering to try and get an idea if maybe our data indicates what those subpopulations are. And then another reason is to do feature engineering with a categorical variable for the clusters. All right, so cophenetic correlation measures the correlation between the distances between our observations and the lowest height on the dendrogram where the points are in the same cluster. All right, so let's go ahead and run through an example. The example I'm going to go through is from the City of Orlando's website, their open data project. This is officer-involved shootings. So here we are just loading the data, and here's what the data looks like, the raw data. And you'll notice I've got some text fields inside my numeric data, and I have some missing values, so we'll need to clean those up. So to clean them up, you'll notice that I have multiple entries for some of the cells, like here. When I have multiple entries, I'm taking the median value inside that cell. And then when we have missing values or we have character strings, I am replacing those with the column median. I'm doing that here. And you notice I'm using the fill in A to impute. And so now I have my cleaned up data. Now, when you're clustering, almost always you want to make sure that your columns have a constant sample variance, sample standard deviation. The sample variance can end up being like the weight of the amount of influence that the column has in your clustering algorithm. And if your data is on different scales, this can make it so that some columns get virtually ignored and some have way too much influence on what's going on. So to even it out, we're going to go ahead and use the whiten function. What this does is goes through and this rescales our data so that we have a constant standard deviation across all of our columns. And so here is our output. And here I'm just showing to make sure you know that I have constant standard deviation for all of those columns. This means that all columns will have equal influence on my modeling. Okay, so now what we're going to do is I'm going to do my hierarchical clustering. Remember, I have two choices when I do hierarchical clustering. I have a distance and I have a linkage. The distance determines how far, or it measures how far any two observations are from each other. And there's multiple ways to go about this. Here are all the different ways that you can run it in SciPy. For this video, I'm just running these three. If you don't know what metric to use, go with Euclidean. Now, after I have my distance matrix, giving me the distance between observations, I need to choose a linkage. The linkage determines how and when observations are grouped together into clusters. And in SciPy, we have these options, but I'm only going to run these three: centroid, complete, and median. So what we're going to do, we're going to take Chebyshev, Euclidean, and correlation distances, and we're going to take centroid, complete, and median as our linkages, and we're going to build some models. So here, I'm going to have 3 times 3 hierarchical clustering models. So we're going to have a total of 9. And this is how I proceed in real life when I'm at work. When I need to do hierarchical clustering, I run through multiple models, I check them out, and I choose the one that fits my situation the best. Now, if I'm doing outlier detection, honestly, I probably could just get away with doing single linkage. That usually does a good job of outlier detection. Ward's linkage does a good job of giving me relatively even, so I'm waving my hand like this, or less uneven, probably a better way to say it, less uneven clusters. So if I want to do segmentation with relatively close to even groups size, then Ward's linkage is a good choice. My experience with scientists is that by far they prefer complete linkage. So choose the one that works best for you. I chose the metrics and the linkage for this video based off of running the code beforehand, and you'll get to see the output of what's going on. I picked these for a particular reason. All right, so now what we're going to do, we're going to go through and we're going to do the cophenetic correlation. So this is coming from SciPy, cluster, hierarchy, and the actual function name is cophenetic. All right, so when we pass something in, we want to give the hierarchical clustering. And then if we want, we can give the original distance matrix that we have for that. And so I'm going to give both. If I get more output back if I give the distance. So if I want the cophenetic distance, and that's all I need, I don't need to give the original distance matrix. You probably have it laying around anyway. If you're working on a project, I feel like you should put it in. But you could save a little bit of time. So the cophenetic correlation, you'll actually only get that back if you give the original distance matrix in there. So my parameters, my linkage, my distance array, what I get back is a matrix of cophenetic distances between the points, or between the rows of data, and then the correlation. All right, so let's go ahead and just take a look at Euclidean distance with complete linkage. This is the model that you should run if you're short on time, or if you don't know what to do, you don't know how to proceed. This is always a good default. Euclidean distance is by far the most common distance in mathematics, so people are ready to accept it. And complete linkage is accepted by the scientific community. It's frequently the default linkage in a lot of programs like in R. So it will be well received. All right, so when I look at this, we see that we have a 0.76 correlation between the original distances and the height where points are merging together. So let's take a look at what the output actually looks like. So here, this is the height where, oh, whoops, I went a little bit too far. All right, so here's the original distances between our points. So here's the Euclidean distance between our rows of data. So this is the distance between first and second, first row, second column. So it's first observation, second observation. Down here, this is the distance between the last observation and the second observation. Now, down here is the cophenetic distance. This is the height on the dendrogram where, for the first time, those two points are in the same cluster. This is the lowest height on the dendrogram where first observation and second observation are in the same cluster. Now, to show how this was computed, let's go ahead and take these matrices, take their original values, drop them into Pearson correlation and see what happens. Let's compare it to this. So the original is 0.756. If I run Pearson correlation on the original distances between rows and the height where observations meet, I get 0.756. That's not a coincidence. All right, so let's go ahead and visualize this. Let's see what this actually looks like. So we're just running Euclidean distance with complete linkage. Now, something I want to point out here is you'll notice that this is the Pulse nightclub shooting. There was an officer-involved shooting at that horrible incident. Oh, and this is kind of off by itself. It's a very, very different event than the rest of the officer-involved shootings. And we can see it here, but we see that it's not completely alone. There is another observation in there. If you look at this observation, there are clear data entries into here. This is saying that like the age of an officer is 56 and their tenure, they're 58 and their age is 58. Their tenure in the Orlando Police Department is 56. So they're saying that they joined the police force when they were 2 years old. There's obvious data entry errors on here. Now, I could go in and fix that, could go and look that up. If I was doing a proper full study, I would do that before I would show anybody these results. Now, I left it here because this verifies that hierarchical clustering is good for detecting problems in your data. I spot an outlier of the Pulse nightclub shooting, which was the worst shooting incident in the United States at that time. And then here, this is a clear data error entry. So, this is working to point out where there's problems in the data. Okay, so now let's go ahead and build a data frame showing our metric, our method, and the correlation that we get. This way, so remember, at this point, we've built 9 different models. I've built 9 different models, and I want to see which one has the best correlation, which one has the worst. That way I can make an informed decision on which model to actually use at work. So what I'm going to do, I'm going to form a dictionary, and for each distance and metric, or distance and linkage. So here I have linkage and so for each distance, each linkage, I'm going to go through, I'm going to make a data frame row that has the metric, that has the linkage method, and then has the correlation on there. Then on this step, what I'm doing is I'm just setting everything up in a data frame to be nice and clean together. Notice I'm doing a transpose that was needed for this. And then I'm going to go ahead and sort the rows by the correlation so it's easier for me to interpret. All right, so when I look at this, I can see that the correlation metric with the median method only gave a 0.4 correlation. Kind of low, 0.4, I mean, that's not much. While Chebyshev with the centroid gave a 0.93 correlation. That's pretty strong. So if the cophenetic correlation is super important for my project, that is, it's important for the dendrogram height to correspond well with the original distances. If that's important to my project, I want to use Chebyshev distance with centroid, with a centroid linkage. Now, something I like to do whenever I have categorical data, I have a numeric variable that I'm interested in. I like to order my categorical data by the numeric variable of interest in terms of the mean or the raw value, something like that. So here, all I'm doing is that I'm taking all those metrics and I'm sorting them by the average of the correlation that we got. All right, so remember, for each distance, we did 3 linkages. So what I'm going to do here, for each of those metrics, I'm going to take the average of the 3 correlations, and I'm going to say the metrics are going to be ordered in that manner. And then I'm going to go and do the same thing with the linkage. With the linkage, each of them also got 3 metrics. I'm going to order the linkages by the average of their correlation. That way it's a little bit easier to visualize in a moment. So here I'm going through and I'm just ordering things, ordering the linkage by the correlation. Notice I'm doing a sort values. So I'm grouping by the method. I'm taking the correlation average. I'm sorting by the correlation, and then I'm grabbing the names. And so here we can see that overall correlation, ironically, gave me the weakest average correlation. Chebyshev gave us the greatest on average. That was of the distances. Of the linkage, median gave us the lowest correlation on average. Centroid gave us the largest on average. And now I'm visualizing a bar plot for each of these. So we can see that centroid did about the same every single time. And we can see that median had the largest correlation when it was paired up with Euclidean, the lowest when it was paired up with correlation. And we can see that complete linkage, had a bit of a difference across the 3. Now, if I reorder things, regroup them, we can see that how centroid definitely had the strongest, or the strongest correlation across the board. All right, so it would be important to me that now how I can use this going forward. Let's say that I have a client who's not comfortable with Chebyshev as the distance. They don't understand it, they don't know it, they're not familiar with. I know that the Euclidean would not be a bad choice. So here, Euclidean with centroid linkage would be a good choice for maintaining a strong relationship between the dendrogram height and the distances on my correlation matrix, or the values on my distance matrix. All right, well, that's all I've got for you. Take care and goodbye.